Hi everyone, my name is Daniela Massiceti and I'm a machine learning researcher at Microsoft Research in Cambridge. And today I will be talking about how we can use Fewshot learning to realize teachable AI systems. We are moving into a technological era that is setting up the world just for me. I can adapt my work tools to benefit and reflect me. I can become a virtual avatar that looks just like me in a meeting. I can get entertainment suggestions that are perfect for just me, and soon even my healthcare might be personalized to me and my exact genetic makeup. But is me really me? As we start to look critically at the AI technologies that underpin these personalized experiences, we realize that how AI systems represent me is actually only a coarse-grained version of me. For example, the coarse-grained category of gamer may no longer fit for a new dad who now wants simpler games that allow him to divide his attention more easily. Or the coarse-grained avatar for man may be insufficient for a veteran who no longer has his right forearm. Let's take me as another example. An AI system may place me in the coarse-grained bucket of woman. We define this bucket by a whole set of features that we typically associate with a woman. That she likes beauty and fitness, that she's good with people, that she likes high heels and buying clothes, that she wants to have children, and many more. But if we dig a little deeper, we may find that these coarse-grained buckets do not capture all the facets of our identity. Some features may be missing from the buckets. So, for example, that I'm South African and growing up in South Africa has a much stronger influence on my identity than, say, my gender as a woman. Or that I work in tech and I've been coding from a very young age, which perhaps doesn't commonly appear in the bucket of women. Also, some features in the bucket may be irrelevant. For example, that I don't care much for high heels anymore after spending the last 18 months shuffling around at home in my slippers. Or that I don't like buying clothes, I prefer to design and make them myself. Just like me, millions of people may find that they do not fit into one of the coarse-grained buckets that underpin many of our AI technologies today. Yet, we have wholeheartedly adopted this bucket-based approach in AI. Perhaps because it aligns with how we as people also tend to group other people into buckets to help structure our view of the world. However, by doing so, we may be creating AI systems that, far from serve many people's individual needs or appropriately capture their identities. Let's take Lindiwe, for example. Lindiwe was born in South Africa, and she works as a data labeler for a local annotation company. The company has just signed up for a virtual meeting tool so that they can connect their Kenyan and South African offices more easily. The functionality is overall great. However, Lindiwe is running into a few problems. She likes to turn the background effects on whenever she's in a meeting. She knows that there's nothing more unprofessional than having one of her boys running into the room or one of her colleagues eating lunch in the background when she's in a client meeting. However, the background effects don't always work for Lindiwe. She likes her hair in an afro, but the segmentation doesn't capture it well. She also likes to wear a traditional headscarf and earrings on some days, but it doesn't work well for those either. Instead, every morning, Lindiwe has to strip back some parts of her identity so that the technology will work for her. If only there was a way that it could be personalized to her so that she could express her full identity more freely. Now, as responsible AI practitioners, every time we come up against such an example that seems unjust, we try to rearrange the buckets. We add more buckets, we take buckets away, and we reshape the buckets. We may feel satisfied for a while, until the next example of failure comes off the queue, and we must begin again. For example, in Lindiwe's case, we might decide to break the bucket of women into women with a dark skin tone and women with a light skin tone. But actually, a woman with a dark skin tone who comes from America versus South Africa may be quite different, so perhaps we also need to split by location. But after we've done this, we may find that a South African woman with a dark skin tone shares many features with other groups of women in South Africa. So perhaps we need to add another split or merge these buckets somehow. And so we can go on and on. What we each need instead is a bucket of me, in which each of us can choose the facets that represent ourselves. Now, one of the most human attributes is a desire to shape our own identity. A bucket of me is something a person creates for themselves. It is not learned automatically by a machine from simply observing a person or their interactions. Instead, a person must have the agency to capture their own unique needs and the freedom to choose how they want to identify themselves to the world. The vision of Teachable AI is to give each person the opportunity to tune an AI system on their own bucket of me. It is a young field that draws on interactive machine learning and machine teaching, and it enables an end user to tune an AI system to their personal needs and identities through examples and other high-level constraints that they provide. The result is an AI model that is personalized to the end user. To imagine an example of this, let's go back to Lindiwe. First, she would capture a few images of herself and label her silhouette outlines, showing all the aspects of her that are important, her own bucket of me. She would then pour her bucket of me into the teachable system. It will learn her silhouette on the fly, and finally will deliver a model that is personalized to her, one that will be able to segment her correctly and not cut off her headscarf or her earrings. Crucially, Lindiwe is in control of the data she puts in her bucket. So if next week she decides to change her hairstyle, she could update the examples in her bucket and repersonalize her system. But is this vision of Teachable AI just that, an idealized vision? Or can we actually realize these systems? The biggest challenge we face in Teachable AI is that the model must personalize to a new user by learning from only the data that is in that user's bucket of me, a bucket containing only a handful of examples. This contrasts the dominant machine learning paradigm, where systems are trained on buckets containing thousands of examples in each. However, machine learning is on the cusp of overcoming this challenge. Recent Fewshot learning algorithms allow a model to learn completely new concepts from just a few examples, say between 5 and 10. These algorithms have made great leaps and strides in recent years and open the possibility of completely personalized, teachable AI experiences in the future. In the next few slides, I will explain how these Fewshot learning algorithms work in the context of Lindiwe's background effects. If you'd like to dive into more technical details, then the two references I've provided here are a good starting point. The first presents an early vision of how we might build models that have this ability to learn new concepts dynamically in deployment, while the second is one particular Fewshot learning algorithm called MAML, which really kicked off the more recent research in this field. Right, so now on to a very high-level description of how these Fewshot learning algorithms work. At their core, they have two phases, a training phase and a teaching phase. We've already covered the teaching phase. Here, a user in the real world, like Lindiwe, would give the system a small bucket of examples, and the system would use that data to then deliver a model that is personalized to that user. But For us to deploy a system that is teachable in this way, a machine learning practitioner has to explicitly train the system beforehand to know how to handle just a small bucket of data per user. To do this, the practitioner would create hundreds, thousands of buckets of me, each one belonging to a different user and containing, say, a few labeled examples of that user. During the training phase, we'd pick one user at random, and we'd feed in a few of those examples into the model so that it has a chance to learn how to segment that user. Immediately afterwards, we'd feed in a final example as a test and then reward the model if it properly segmented that user. And we'd do this repeatedly for many randomly sampled users in our training set. The result is a final model that is dynamic. Once deployed, it could learn to segment any completely new user by looking at just a few training examples in their bucket of me. We can contrast this with standard machine learning algorithms, which don't group the data by user, nor do they pass it to the model in these mini user sets. Instead, training is done by simply randomly sampling images from very coarse-grained buckets, each containing hundreds to thousands of examples. In contrast, the result here is a static model that has simply rote-learned this fixed set of buckets. So I've presented this grand vision of teachable AI and a class of machine learning algorithms that we could potentially leverage to achieve it. But how do we get started? As we've seen, there is a broad range of applications that could be made teachable toward completely personalized AI experiences. Our team, Project Tokyo, is exploring teachable systems in the context of assistive tools for people who are blind or low vision. We believe that giving a blind user the flexibility to personalize their tools will really drive the next generation of innovation for a community with a diverse set of needs. Building on this, we are excited to announce a new Teachable AI benchmark that is grounded in teachable object recognition for people who are blind or low vision. Similar to Lindiwe and her personalized background effects, a teachable object recognizer will allow a user to add just a few examples of a personal object to their bucket of me. The recognizer will learn this object from just those few examples and deliver a personalized recognizer that can then identify that specific object in any number of new real-world scenarios. And the user could do this for any number of personal objects they have. We couple this benchmark with the Orbit dataset, a new dataset collected by people who are blind or low vision. The dataset is a collection of short video clips of objects captured by blind people on their mobile phones. Importantly, the dataset is grouped into one bucket per user, where each bucket contains the objects belonging to a single user along with their anonymized videos. Now, our initial work on this teachable object recognition benchmark has highlighted the broad set of multidisciplinary challenges that lie ahead of realizing fully teachable systems. And so I'd like to wind down this talk with a discussion on some of these opportunities. First, a sampling of challenges in the machine learning space. A teachable system needs to personalize consistently across users. Fewshot learning algorithms have made great progress so far, but they haven't really been explored within this user-centric framework. Our initial experiments show that the performance of state-of-the-art Fewshot learning algorithms are highly variable across users. For one user, the recognizer personalizes really well, while for another, really poorly, in some cases to as low as 25% accuracy. The second area of focus is that a teachable system needs to be robust to noisy data. A user's bucket could contain mislabeled examples or examples that are just difficult to learn. Our results show that these state-of-the-art algorithms can identify new objects with only 60% accuracy in these real-world cluttered environments, as I've shown here on the slide. These points highlight the need for us to move away from clean, curated datasets and toward more real-world data, and to also think about new ways in which these models can handle data and label noise. This could range from being able to identify and filter out poor examples from a user's bucket, to understanding how these Fewshot learning models quantify uncertainty in the face of these different types of noise. A second set of opportunities lie in the HCI space. First, a teachable system needs to be explainable. As the user adds data to their bucket and personalizes their system, the system should be able to communicate what it knows and what it doesn't know in a way that is easy for the user to understand and then act on. So, for example, it might need to notify the user which items in their bucket may be hampering the model from personalizing effectively. Now, identifying which examples are difficult is a non-trivial machine learning problem, but deep thinking will also be required to know what performance information to draw out of the model to then communicate to the user. A second area of HCI focus is that a teachable system also needs to evolve with the user over time. As they go, a user will add and subtract data from their bucket and will repeatedly personalize their system. This is a shift from the typical paradigm, where models are usually analyzed at a single slice in time, and so we need to extend our understanding to how a user and a model work symbiotically over an extended period. Finally, teachable systems open several research engineering opportunities. First, a teachable system needs to learn quickly, for example, in a matter of minutes, seconds to minutes each time a user edits the data in their bucket. It also needs to do this in a computationally lightweight manner. Both of these challenges are relevant because learning from the data in a user's bucket may need to happen on the user's device, for example, their mobile phone or their computer, perhaps for privacy or other reasons. In our current work, we are explicitly looking at a class of Fewshot learning algorithm that can personalize to a single user by passing their data just once through a deep neural network. This is computationally super lightweight and would allow learning to happen on a resource-constrained device like a mobile phone. So I'm sure you will agree that this Teachable AI vision really presents a wide range of both pure and applied research challenges, all of which offer an incredibly exciting space for those across the machine learning and HCI disciplines. Achieving this vision will not only allow us to realize teachable object recognizers for people who are blind or low vision, but it also has the potential to revolutionize a wide range of other applications, from personalizable HoloLenses on factory floors and in hospitals, to personalizable background effects in Teams. And so with that, I'd like to close with 3 key take-homes. The first is that Teachable AI is a paradigm shift in machine learning, which will move systems from coarse-grained buckets to highly individualized buckets of me, one for each end user. Second, Fewshot learning is on the cusp of making these teachable systems a tangible reality. We need to continue driving research in this space to make models reliably teachable. And then finally, we offer a call to action. We present a new Teachable AI benchmark and dataset and hope that you will join us in exploring the multifaceted and multidisciplinary field of Teachable AI. Thank you to all the amazing people behind this work. And finally, thank you for listening.